Alright, so we have talked about permutations, combinations, and the multiplication rule. We're going to do a few examples using counting and probability. So for the first set of examples, a donut shop has 12 kinds of donuts. You're buying donuts for your 4 friends. And how many ways can this be done? In scenario 1, you're getting a bag of 4 donuts, and all the donuts are going to be different kinds. Scenario 2, you are getting 4 donuts and delivering them to your 4 friends individually, and all the donuts will be different kinds. And scenario 3, you're getting 4 donuts, delivering them to your friends individually, but you could get more than one of the same kind of donut. So think about these, about the number of ways that these donuts can be purchased and distributed in these different scenarios. All right, bag of 4 donuts, you're not giving them to individual people. That means that in this case, the order doesn't matter. So in a bag of donuts, the order does not matter. And all of them will be different kinds. This means there's no repeats. So if there's no repeated objects and the order does not matter, this is N choose K. We have 12 donuts to select from, and we're selecting 4 of them. So this is 12C4 or 12 choose 4. So that's 12 factorial divided by 12 minus 4 factorial times 4 factorial. That's 12 times 11 times 10 times 9 divided by, we already got rid of this by getting rid of the rest of 12 factorial, getting rid of 8 factorial, divided by 4 times 3 times 2 times 1. We could do some canceling. 4 times 3 cancels with our 12. 2 cancels with our 10 to leave 5. So we're left with 10 times, or 5 times 9, that's 45 times 11, which gives us 495. So there are 495 different bags of 4 donuts that we could select, or that we could purchase from these 12 different kinds of donuts. When we do not have any repeated donuts, when we don't have any donuts of the same kind. Part 2, this time we are getting 4 donuts, but we're delivering them to our friends individually. So Andre gets this one, Beth gets this one, etc. So here order matters. Order matters because we are assigning different donuts to different people, and all the donuts will still be different kinds. So this is still no repeats. So this is then N permute K. So there are 12 possibilities for the donut that Andre gets. There are 11 possibilities for the donut that Beth gets. There are 10 possibilities remaining, because we're not doing any repeats, for the donut that, I forget what the C name was, and 9 for the D name. So this is the total number, and the difference between this and the previous is that we're not dividing by 4 factorial, because the order does matter. If we multiply those values, we'll get 11,880. Okay, so last one. Now we're getting 4 donuts, delivering them to our friends individually. So again, order matters. But in this case, you could get more than one of the same donut. So now repeats are allowed. So how many choices do we have for Andre's donut? We have 12 choices for Andre's, and 12 choices for Beth's, and 12 choices for your next friends, and 12 choices for the last friends. So that's 12 to the 4th possible sets of donuts that you could purchase, sequences of donuts that you could purchase. So that's 20,736 possibilities in that case. All right, here are 4 more problems for you to try out, and then I'll go through them one by one. So for the first one, ballots are cast for a green team or a blue team. In a certain polling place, there are 312 ballots cast for Team Green and 285 for Team Blue. If 8 ballots are found mistakenly discarded, what is the probability that they were all for Team Green? Second example, in an escape room, one of the challenges contains 10 different pegs, and there are 3 different slots that pegs go in. The correct pegs must be put in the right order. There's a riddle to help solve which pegs go in where, the team has given up on solving it, and so now they're just trying to place the pegs in. What is the probability that any one particular placement of 3 pegs in slots is correct? Example 3. In a certain lottery, 4 different numbers between 1 and 25 are chosen. To win, you need the same numbers that were chosen, but in any order. What is the probability that a particular set of 4 numbers wins? And last example, same as the previous, except that the order needs to be the same as the numbers chosen. So in this lottery, 4 different numbers between 1 and 25 are chosen. To win, you need the same numbers that were chosen in the same order. What is the probability that a sequence of 4 numbers wins? All right, so for this first example, we've got the probability that these are all green would be, or team green would be number of ways for these 8 ballots to be team green divided by just the number of sets of 8 ballots from this polling place. So what is this? Number of ways for the ballots to all be assigned to Team Green. Well, there were 312 ballots from Team Green, and we're talking about the number of ways to select 8 of them. Why is it choose? Why is it 312 choose 8? It's because there are 8 ballots and they're just found. It's not like they're in some particular order, so there's no order, and you can't select an object more than once. In this case, there's no repeats. So this would be 312 choose 8 divided by the number of ways to select 8 of these ballots that are from either green or blue. So this would be 312 plus 285. And so this is 312 choose 8 divided by 597 choose 8. And so both of those are really huge numbers. This first one is 2.03 times 10 to the 15th divided by 3.82 times 10 to the 17th. And so that turns out to be 0.0053, or about a 0.5% chance, half of a percent of a chance. I could imagine some kind of argument being made about something like this if there is, a set of ballots found after an election, and we don't know whether that set of 8 ballots was just misplaced by mistake, or whether it was misplaced intentionally, and a probability argument like this could theoretically come into play. Next one, in an escape the room, one of the challenges contains 10 different pegs, and there are 3 different slots that the pegs go in. The correct pegs must be put in the right order. So that tells me that, I've got these 3 slots to put these pegs in, and these slots are different. So I've got slot 1, 2, and 3, and these different pegs must be put in the right order as well. So this tells me that order matters, and I can't put something in the slot twice. These are just placed in. So repeats not allowed. So order matters, repeats are not allowed. Because order matters, that's now 10 permute 3. I've got 10 pegs, and I'm picking which of the 3 holes each of those will go into. So in other words, there's 10 possibilities for the first one, and 9 possibilities for the second one, and 8 possibilities for the third one. So 10 permute 3, that's 10 times 9 times 8, and that's 720 possible ways in which this can be done. I was asked for the probability that any one particular placement of 3 pegs in slots is correct. And so the probability that any one sequence of these is correct would be 1 out of 720. Okay, in a certain lottery, 4 numbers between 1 and 25 are chosen. To win, you need the same numbers that were chosen, but in any order. What is the probability that a particular set of 4 numbers wins? So any order, so order doesn't matter. And for different numbers, no repeated elements, no repeats. So that tells us that there are 25 numbers to choose from. We're selecting 4 of them. So this is the number of different sets of 4 values. So 25 choose 4, which is 12, 6, 5, 0. If you calculate it, is the number of sets of 4 numbers, 4 different numbers from 1 to 25. And so the probability that a particular set of 4 numbers wins would be 1 divided by 12, 6, 5, 0. And if you calculate that out, that ends up being 0.00008. So a very small probability of that. Last problem, in a certain lottery, 4 different numbers between 1 and 25 were chosen. To win, you need the same numbers that were chosen in the same order. So now order matters. So order matters, and there are 4 different numbers, so no repeats. And so what is the probability of this? Well, we're still talking about one particular sequence of numbers, so it's still going to be 1 divided by the number of different sequences now of 4 numbers between 1 and 25. So there are 25 choices for the first one, 24 for the second one, 23 possibilities for the third one, and 22 possibilities for the last one. This is the same as 1 over 25 P4. And so if you calculate, so that ends up being 1 over 303,600. And if you calculate that out, that is equal to 0.000033. So less likely still than the event above.